Thanks. I will begin with a word of prayer. Heavenly Father, we thank you again for this time we have together. I thank you for the students, and I just pray that you'd just glorify, you be glorified rather in what we do. And again, Lord, we just thank you for all the many blessings that you bring to us, Lord. In your name I pray. Amen. All right, so I'll talk about these a little bit later. I think they're correct. I mean, so I asked you to calculate the speed. So, well, let me just talk a little bit about it, and we'll come back to these. But first of all, this was a line, right? And so the speed of a line is just the length of its direction vector. So the length of this direction vector is square root of 56, as it happens. This thing is actually also a line parametrized in a weird way. See what this is? This is the point 135, right, plus e to the t times the vector 2, 4, 6. So as a point set, right, if you look at positive time, these cover the same set of points, I think, because, well, maybe that's not quite accurate. If I let t, let's see, what is e to the t? What's the range of e to the t? Can e to the t be minus 1? No. Can it be 0? Not even that. So as you let t, if you let t go to minus infinity, right, you get to the point 135. But to include the base point, you'd have to let the time approach minus infinity for the second one, right? In the first one, if you plug in time 0, you're at the point 135. But geometrically, you know, it's the same set of points. It's this. Well, no, it's not. I mean, how am I going to? I got to draw a picture. So here's the whole line, right? So this might be t less than 0. Here's t greater than 0. And here somewhere is t equals to 0. That point is, as I was just saying, 135. So that's what this line looks like, just sort of generically speaking. In contrast, problem 2 is it's part of this, but actually it's like this, right? We don't include 0, technically speaking, and we get like that. So this would be something like maybe let's call this R2 of t. Right. And that's kind of an interesting curve. Problem 2 and versus problem 1 is, while, you know, half of the line, they agree in terms of the set of points they cover, this one has constant speed everywhere, right? It's always about going at about rate 7.5 meters per second, miles per minute. I mean, whatever your favorite system of units is, I don't care. Let's say it's got speed square root of 56. On the other hand, this guy, well, this is cardinal sin of me taking off. I mean, only half credit. Look at this. Look at this. You gotta. It's non-negotiable. That's got to go over that. So, but this is actually e to the t times the square root of 46. Wait a minute. One of these is wrong. I'm just kidding. Like I said, just, you know, try to do your best. I do these things too. But yeah, 16 plus 36 is 58. 58 plus 4 is 56, yeah. What? Wait a minute, 48 plus. Like I said, I'll make these mistakes too. All right. It's okay. Anyway, we can, but the larger point here is that this speed, what happens as time goes to infinity, the speed gets, I mean, as time increases, the speed gets larger and larger and larger and larger, right? So in some sense, like, the same set of points is covered, right? But you're going faster along that set of points with the second parameterization. So this one here, you might recall, this is the helix, right? And even though this is going round and round and wrapping around the z-axis, always turning, always twisting, always going up, somehow, nevertheless, the speed is constant. Right? So we can have constant speed for very interesting curves. And we can also have speed formulas which are just awful. And you really can't do much to improve on it. This can happen. This formula for the speed doesn't have to be nice. It could be awful. Here's a kind of awful one. All right? So I want to talk to you guys about arc length. So here's the problem that we want to consider. You've got a point, and then you've got another point, say P1. You got point 1, point 2. We have a path connecting point 1 and point 2, where the parametrization R is going to be a mapping from the closed interval T1 to T2 to the path. And I guess I should give this, let me give the set of points that the path covers a name. Let's call that set of points C. So the image of this is C, and let's say it's a subset of, we'll say R3. You could do this for Rn, but I'll just say R3. Okay. So if you want the set theory of it, what I'm saying is that R, when you feed it the set of points T1 to T2, the output of the parameterization is C. C is the set of points which is covered by the parameterization. All right. R is a path. It's a parameterization of a given curve. Do I have everybody's homework? Yeah. I think I do. I have everyone's homework already? Yeah? No? I want to make sure I get them because I don't want to. No, I do not, but I'll take it. Oh, yeah, name would be wise. All right. Yes, because I should generally make a policy of taking off some amount of credit if you give it to me at the end of class. Otherwise, what inevitably will happen is some subset of you will make the foolish decision to work on your homework during class and as to earn extra points, and thus ignore the lecture, which is, of course, something I would. Just kidding. I'll try to protect you from the grader. I don't know. Let's see here. The fuzzies, you know. But these are the fuzzies. See? The fuzzies. See? Those are the fuzzies. I will get scissors myself and cut them off for you. Don't worry. Your secret is safe with me. So I don't actually grade your homework. I give it to an undergraduate who looks at my solution and judges the logical similarity of yours to mine. Hopefully mine's right. Ideally, this grader also finds errors in my solutions. Like, this is one of the things I look for in a grader, right? If the whole class has 3 and I have 2, you should doubt my solution. This is something I look for in a grader, right? Critical thinking. There is a subset of graders here who just don't think. They just say, oh, well, everyone's wrong. No, I'm human. I make mistakes. It's true. All right. I am human. It's true. All right. So we'd like to. This is a path connecting point 1 and point 2. We're given a parameterization. We're given a parametric description of it, right? And the question is, our task. Calculate the arc length of C. Now, what do we mean by arc length? You know, if you had a string, right, and you took that string and you laid it along the path, right, and then you took that string and you just stretched it out straight, however long that string is, that's the arc length, right? Now, here's what you can do is just think about, and I'll just draw another path down here for the sake of making my picture a little bit more dramatic. So what could we do? What would be a strategy for approximating the length of the path? How about we replace the path with a polygonal, a broken line segment, if you will. So just pick points, every so often along the path, like so, right? And if we replaced this path with this set of line segments like this, thanks, sir, then if we calculate the length of each line segment, right, and add up the lengths of all those line segments, that should be kind of a decent approximation, right? If we take enough subdividing points, right? So let's just focus in on how would we calculate the distance between a given pair. So let's call this, the I plus 1th point, and this is the ith point. What would the length be between that? What would the length? And so this displacement vector, we could say is delta Ri. All right, so delta Ri should be what? It should be R of I plus 1 minus R of I. Agree? So that would be R of, let's say, Ti plus 1 minus R of Ti. So I'm assuming that this is at time t sub I, and this guy is at time t sub I plus 1. I now regret calling these T1 and T2. Could you guys give me a better label for those? Like maybe time A and time B? How about that? See, because it's interfering with my labeling. Oh, I said A and B, but what I write? Idiot. B. So this P1 is R of the initial time A, and B2 is R of the final time B. So this first point here would be, where do you want to start the numbering? If I start at 0, that's kind of nice. This would be R of T naught, right? So this would be, I don't know. We guys want to start numbering at 1 or 0? Choices. Start at 0. All right. This is R of T1. So what's this first displacement vector would be delta R naught. This one would be delta R1. This is delta R2. These are the displacement. The sum of all these displacements gets us from point 1 to point 2. All right. So again, let's focus our attention here on the ith displacement vector to try to understand what that looks like. Okay. So what I can do is I can calculate that this is also equal to R of T I plus 1 minus R of Ti divided by delta T times delta T. Where here I'm supposing that, delta, so let's just let's make the added assumption that the times that I'm chopping it up into, they're equally distributed. So like delta T in my setup, what would delta PT be? Poor planning on my part. I'm going to write it up here. Sorry, guys. Where delta T would be the total time, which is B minus A, divided by the number of segments, which would be, let's call it N. Right? Now, this actually, if we look at it more carefully, we could look at it as, this is x of time I plus 1, right, minus x of time I, divided by delta t, comma, y of time I plus 1 minus y of time I divided by delta t, z of, you guessed it, time I plus 1 minus z of time I divided by delta t, all times delta t, using x, y, and z for the x, y, and z components of the path. And then what I'm going to do is I'm going to make an extra assumption. I'm going to assume that this path is not just any old path. I need that the path is got derivatives of the component functions which are continuous. So I'm going to assume that the derivative of x, y, and z exists and is continuous. If I do that, then I can apply the mean value theorem. I can apply the mean value theorem on the interval mean value theorem on the interval t sub I less than or equal to t less than or equal to ti plus 1. I can pick a t sub star, a ti sub star. You know, I can say, well, that's really dx dt of ti star, dy of t of ti star star, and dz dt of ti star star star. The reason for the star star and star 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 is because I'm separately applying the mean value theorem to each component function one at a time. And there's no reason that the time at which the instantaneous rate of change matches the average rate of change has to be the same for all three component functions. In principle, it could be different. But all of these, ti star, ti star star, and ti star star star, have to be an element of, you know, ti to ti plus 1. Sorry, it's getting so small down here. There you go. In other words, what I'm saying is if you apply the mean value theorem 3 times, you can actually find a path version of the mean value theorem. See, this is really nothing more, well, in the limit as the time goes to, as delta t goes to 0, what happens? I hate to erase this, but I'm going to have to. I wanted to use this as an example, but it's too late. I'm going to save these, though. All right, getting to it. We have that delta Ri, right, is equal to, oh, well, maybe I should take this, the limit as delta t goes to 0, right? Still not what I want. I'm sorry, guys. I'm trying to avoid writing so much. I guess I just need to bite the bullet. What's the length? So what is the arc length then? It should be, S should be equal to the limit as n goes to infinity, right? Of the sum, I equals 1 to n. Oh, what did we decide? I equals 0, right? 0 to n. Of what? The length of delta r sub I, right? I mean, that's just the geometric idea. We take the sum of these lengths and take the limit as n goes to infinity. That should give us the arc length, right? But if you look at what we just derived, we can rewrite this as the limit as n goes to infinity of the sum I equals 0 to n of what? The square root, right? Well, let me just, let's stick with the magnitude of that vector, right? dx dt, ti star, dy dt, ti star star, dz dt. Oh no, my next example is in danger. Ti star star star. So sad. Goodbye, example. I was going to set up the arc length with it, but alas. Oh well. So this, excuse me, times delta t, right? But by properties of the length of a vector, you notice that we can pull this delta t outside the length of the vector, right? Like I have this vector times delta t, that's a number. I can pull it outside the vector length. And we're assuming it's positive, so we don't even need to put an absolute value there. Right? What happens in the limit as n goes to infinity here? Well, anyway, the point is that that's the Riemann integral of a particular function. By definition of the Riemann integral, this is actually the integral from a to b of the length of, well, this thing, right? dt. Sorry. And to be entirely nicer formula, how about integral from a to b of v dt? Because that's the speed, right? So the assumption that the path is has continuous derivatives is kind of important. An example I always show my calculus 2 class is the following. If you had this, if this is 3 and this is 4, we'd all agree that if you go 3 over this way and 4 up that way, it's 7, right? But what happens if you take this to go half of the 3 and then like this and like this? So you follow the stair step. It's still length 7, right? You just gone half of 3, 1, and half of, you've gone 1.5 horizontal, then another then 2 vertical, then 1.5 horizontal, then 2 vertical. The path length still 7, right? And then if you subdivide further, the stair step, it's still got length 7, right? And if you subdivide further, the stair step still has length 7. What's the limit of the stair steps? Keep doing this. Just keep doing it and doing it and doing it and doing it and doing it. Eventually you get to this, right? So apparently the length of the red dotted line, because it's the approximate, right? It's the approximate of the stair steps. And the limit is the number of stairs go to infinity. So the length of the red dotted line is 7. Disturbing, no? Because it's not 7. What is it? Yeah. But it's 5. It's not equal to 7, which is somewhat troubling. Being careless about limits can lead you astray. This is a good example of that. The error in that is that this is not a path in which you can infinitesimally essentially apply the mean value theorem. So this calculation breaks down for that. The assumption that the derivatives are continuous is a necessary one. Anyway. But I won't ask you to calculate the length of a infinitely subdivided stair step anyway, so you're probably fine. But on the other hand, check it out. Now we have a formula for the arc length. What is it? Definition. The total arc length is just equal to the integral from a to b of the speed dt, given this setup. Now, we can also talk about the arc length function. Definition for nice path. Let's say for path r, all right, going from, say, I don't know, time 1 to time 2, all right, to wherever. It doesn't have to be r. I did this derivation for 3 dimensions, but actually this derivation works just as well for 2 dimensions or for 4 or for 5 or for 6. There's no use of the cross product. It just involves the length. Length of a vector is defined in n dimensions, just the same. But anyway, so for a path going from, say, t1, t2 to Rn, the arc length function function based at t1 is given by s of t equals to the integral from t1 to t of the magnitude of dr see, now here's where I get into trouble. We've used t as an arbitrary variable of integration, right? I mean, it's a bound. So I can't use t for the integration as well. I needed a different symbol. T bar or tau? What's your choice? Tau? All right, tau it is. If you like, you could replace tau by u. Some other letter. Just we shouldn't use t because t has a fixed but different meaning. So this is the arclength function, right? All right, so for example, this one over here, right? This example that I had you guys work out, this helix. For the helix, if we say, let's add some fine print, let's say for 0 less than or equal to t less than or equal to 2 pi, right? Then that would say the total arc length is what? Integral from 0 to 2 pi times the speed, which is what? You guys worked it out already. Square root of r squared plus m squared dt, which would be what? This kind of integration is like the best. Integral of a constant over some region is just the length of the region times the constant, right? I mean interval. I shouldn't say region. I should say interval. Of course, this is also what? This is also the arclength function at 2 pi, isn't it? The arclength function based at 0, though, right? People are kind of careless. They'll, you read a book, it'll say, calculate the arclength function. Oftentimes, they won't tell you where the base point is. So our default is if we don't tell you where it's based, we just assume you're going to start it where usually start it at 0, or you'll start it at the left endpoint of the interval. That's the sort of the custom. Here's the other one, s of t. So that would be the integral from 0 to t of the square root of r squared plus m squared d tau, right? Which is the square root of r squared plus m squared. What's the integral of d tau? Well, it's tau. You evaluate that from 0 to t, just to make it look like I'm really doing something here. I'll write down my work. So that's t times the square root of r squared plus m squared. And I'm writing the t before the square root as to not be accused of the same carelessness which I was making fun of about 20 minutes ago. Be careful with square roots. What's inside the square root versus what's outside the square root. It is a thing that people are very vague about sometimes, and it causes me trouble in my grading. There you go. There's the arclength function, right? T times the speed for a constant speed curve. Now, what would the arc length be for this problem 4? What's the length of the arc? What would the arc length function based at 0 there be for this example? S of t, right, would be the integral from 0 to t of the square root of sinh squared tau plus cosh squared tau plus 4 tau squared, d tau. And there you go. That is the arclength function, and that's about as good as I can do. So sometimes you can't actually calculate the arclength function if the curve is too complicated. And yet we can describe it by an integral, always, right? All right, so what is the relation between the speed and the arc length? I've told you it's the magnitude of the velocity, right? But let's use a little calculus. There's more we can say. Check this out. Theorem. V is equal to ds dt. So let's derive that. How do we derive it? Well, set up the arclength function like that. We take the derivative with respect to time of the speed, right? So that's d dt. Oh, I'm sorry. Look at this. This is sad. Look at that. I mean, this is no s, right? Differentiate the speed. S is not for speed. S is for arc length. Yeah. See, there's a pitfall right there. So I didn't invent the letters. I'm just teaching it. Integral from say t1 to t. So I'm setting it up. Bless you. Setting it up in the same notation as what's right above it. Okay. So I'm assuming that the path is got, you know, the derivatives exist, so the arc length function makes sense, right? And now this is what I mean. That's the definition of arc length, based at 0. I'm differentiating this. How does that work out? What is this? This is like ddx, right, of the integral of f of t dt from a to x. What's that equal to? F of t. F of x, yes. Now, of course, here tau is playing the role of t, right? And we don't have an x, we have a t, so t is playing the role x does up here. This is the fundamental theorem of calculus part 1 or 2, depending on the textbook you look at. But in my default, it's 1. Anyway, the point is that that is equal to the magnitude of dr dt by the fundamental theorem of calculus, part 1. And what is that? That is what we defined to be speed. That is v. And isn't this beautiful? I mean, so what we have is that v is equal to ds dt, right? And so there's a beautiful circle of ideas here in the sense that once you know that, if you accept this, perhaps you could even take that as a definition and then use the infinitesimal method. See, this would say then that ds is equal to v dt, right? So if you want to calculate the arc length, integrate the arc length, how do you do that? Well, you integrate the speed times dt. That's how you actually do it. But I've derived that v is equal to ds dt today. Yeah.
So in the theorem, the s in the ds over dt is referring to the arc length?
Yes, s is the arc length based at time 1. You notice that it doesn't matter what time we base it at either. The derivative would work out the same. Yeah. Okay? Yeah. Where did I put my... Yes, you knew. Thank you. So let's do another example. Suppose we look at the twisted cubic, right? That was r of t was t squared, t cubed, right? So what's my velocity? What's my speed? What's my arc length function based at 0? Let's figure these things out. So velocity, v. We got 1, 2t, 3t squared, right? And then what's my speed? My speed, square root 1 plus 4t squared plus 9t to the 4th. Not especially nice. I mean, I don't think I see that. Do you see that simplifying? Can you factor that into like a square? I don't think that's going to happen for us. And then so anyway, here it is. S of t is the integral from 0 to t of the square root of 1 plus, I'm tired of tau, I'm going to use a u just to mix things up here, 4u squared plus 9u to the 4th. Of course, you could put u equal to tau if you prefer it. It doesn't really matter. It's a dummy variable of integration. You could put Pac-Man here. It wouldn't be any different. There's only one thing you can't do here, which is what? T. That's the only thing that logically we shouldn't put there. So it's what you'll put there. No, let me not. That'd not be a self-fulfilling prophecy. There you go. That's the arc length as a function of time for the twisted cubic. Yes, sir?
Should the t still be in the interval then?
T still be in the...
Interval from 0 to t?
Oh, yes. That t is necessary. That's the same t that's appearing here. For example, what's the arc length from 0 to 0? It's a lot of writing, but what is it? It's 0, right? There's no, how far is it to get from where you're at time 0 to where you're at time 0? 0. But if you put a 1 there, you know, it work out something. Any question? I thought I saw a question. I did not. All right. All right, so next order of business is, so this is one interesting aspect of the geometry of curves, right? The arc length. And sometimes we can actually calculate the arc length function explicitly, and sometimes we can't. Here's an interesting thing. If you can calculate the arc length, if you reparameterize the curve using arc length, something really neat happens. Let me show you that for just a second here. Reparameterize. Reparameterization. What's that about? So we can look at, for example, let's look at the helix. We had r of t was r cosine t, r sine t, mt, right? And we found that the arc length based at 0 was, what was it? It was just t times the square root of r squared plus m squared. So we could find a different parameterization of the helix, which was using arc length as a parameter. Here's how you do it. So to parameterize the helix with respect to S, simply solve star for t, right? So that gives us t equals to what? T is equal to S divided by the square root of r squared plus m squared. And then what you do is you take the parameterization you already have and you simply plug that in the place of t. So let's call this R2 of S is going to be equal to r cosine of what? Not t, but S divided by the square root of r squared plus m squared. And then I do r, the sine of S divided by the square root of r squared plus m squared. And then I do ms over the square root of r squared plus m squared. What I just did is known as the unit speed parameterization of the helix. You say unit speed. Why would you say unit speed? What does that mean? Why is this the unit speed parameterization of the helix? I mean, basically I'm saying, in this thing I just wrote down, S is playing the role of t, right? So if you can, kind of forget about the t for a second and just look at R2. Right? Just look at R2. So what should the speed of the path R2 S maps to R2 of S, what should that speed be? Let's not guess, let's calculate it. How do we calculate the speed? We want the magnitude of what? dr2, right? ds. So that's the magnitude of what? We got to differentiate, right? What do we got? We got minus r divided by the square root of r squared plus m squared, right? Sine, oh, such a pain. If you don't mind, can I just call that thing theta? Let me just, if you don't mind, I'd like to call this thing theta for the sake of not writing it. And then differentiate this with respect to s. What do we get? R over the square root of r squared plus m squared. Derivative of sine is cosine. The inside's still theta. Right? How about this last thing? When we differentiate the z component of the unit speed helix with respect to s, what's that give us? Differentiate that with respect to s. M and r are constants. What happens? We just get m divided by the square root, right? Can you simplify that vector? What is this vector? Look, there's a common factor, 1 over the square root of r squared plus m squared, right? This is a positive constant, so we can pull it outside the vector length function, right? And what's the length of the vector that I'm about to underline in red? What's the length of that vector? R squared sine squared theta plus r squared cosine squared theta plus m squared, also known as? Divided by? So what's this? Can you fill in the blank now? Fill in the blank, right? This is equal to 1. The speed of this is 1. It is called a unit speed reparametrization because if you reparameterize the curve with respect to arc length, it makes the speed be 1. And that starts to make a lot of sense if you just think about, so the speed, right, is ds dt, right? When t equals to s, what happens? We get v is equal to ds over ds. What should ds over ds be? It seems like it should be 1, right? So if we put t equals to s, we get unit speed. I could have just written that thing I just wrote in green and tried to bully you into believing it, but I think it's better for us to actually look at an example and see how that actually plays out. All right, that's a reasonable. If I ask you to reparameterize a helix with respect to unit speed, that's a completely reasonable question. If I asked you to reparameterize this thing with respect to unit speed, would that be a reasonable request? I don't think it would, because you'd actually have to solve, you'd have to somehow do this integral and somehow to invert that equation to write t in terms of s. So if you can't do the integral, it's hard to find the concrete formula for, I mean, it was simple to solve this for t, right? We just had to divide by that speed. For an arbitrary curve, it might be very difficult to do that algebra. Nevertheless, theoretically, it's always possible, at least in principle, to find a unit speed parameterization of a curve. All right? I always forget when this class ends on Tuesday, Thursday. It's 2, right? Yeah, so we have ways to go here. Okay, so let me tell you where we're going. There are 2 things. The one is I need to describe to you how you calculate the parameterization for a tangent line to a curve. That's a pretty simple thing. And then the other thing I have to describe to you next is what's called the Frenet-Serre equations and the so-called Frenet-Serre apparatus. That's a very interesting thing. That'll take me much longer to completely develop. It'll probably take me about an hour of lecture total to unwrap that. So what I'm going to do right now is I'm going to show you how to find the parameterization for the tangent line, and then we'll start the TNB thing. TNB is the Frenet frame. So let's talk about tangent lines to start with. Arguably, this should have gone before here. I don't know. So suppose you want to find the equation of the tangent line. So here's, r of t. I want to find the, well, not equation for the tangent. Do you want to find the equation for the tangent line in 3 dimensions? You'd have to say, no, I want to find the equations for the tangent line, at which point you realize, no, I don't want to do that. I want to find the parameterization because that's easier. So tangent line would be this, right? And so geometrically it's that. The direction of the tangent line is simply, by definition, the velocity vector. So let's say this. Let's suppose that this point here is r of time t naught. So L should be something like r of t naught plus t times r prime of t naught, such that t is a real number. That's the tangent line as a point set. Now, the parameterization of the tangent line, if I want a colliding, the so-called colliding parameterization, then what I would use r of t is r of t naught plus parentheses t minus t naught times r prime of t naught. Again, this is the velocity at time t naught. The reason I say colliding is then, oh, and I shouldn't use r of t here, right? R of t is the given path. I need a new symbol for the tangent line. So what do you want to call it? Let's say L. The tangent line, L of t if you like. You notice with this setup, what happens when we put L of time naught? What do we get? This is 0, right? If t is t minus t naught 0, and so we just get back r of t naught. So in this sense, they collide at the same parameter time. At time t naught, the path and the tangent line are at the same point. In this right here, which you might, I mean, this thing I have right up here, this would be a possibly non-colliding parameterization. In the sense that maybe the path gets to the point at time 1, whereas if you write that formula, that puts the tangent line at the point of tangency at time 0 with what I just squiggly underlined. Let me give an example. These things are better if I give you an example. Stink. I guess I'll just ask you guys in words before I forget. Can you tell me anything interesting about the arclength function? Skipping back just a second, my brain sometimes skips. Something I forgot to ask you about. Can you tell me anything special about it? Like, is it decreasing? Is it increasing? What can we say about it? Think calculus 1. So the arclength function, right, the derivative of it is the speed. What's the smallest the speed could be? 0. Usually it's what? Positive. So if you think about it, we can easily prove that the arclength function is increasing, which is not especially surprising, but just saying, it's there. That's important because that means that in principle, at least logically, you can, even though you can't find a formula for s as a function of time, if it's strictly increasing, that means that if I plot t this way and s this way, then the arclength function, it starts wherever it starts at 0, it starts there, right? But then it has to do something like that. It can never come back down. It has to satisfy the horizontal line test. It has to be an injective function. So even though, yeah, I can't find the formula in that last example, logically, an inverse function does exist, even though I can't find a formula for it. Logically, it's there in principle, theoretically, to find, which is important. That means that you can always find an arc-length parametrization for a curve, even if you can't find it with equations. Logically, it's there. All right, so I'm sorry, I feel obligated to say that to you. How about the twisted cubic? That served us well. So we got, I just erased it, an idiot. R of t. Here, let's switch it up a little bit. T squared, it's no longer the twisted, I don't know what this thing looks like, something else. But it probably is also kind of twisted. I want to find tangent line at 1, 1, 1. So what time would that be for this path? What's that? Yeah, time 1, right. T equals to 1 gives R of 1 is 1, 1, 1, right? So then all I need to do is to calculate dr dt, right? Which is what? It's 2t, 3t squared, 4t cubed. And then what is r prime of 1 then? Yeah, 2, 3, 4. So therefore, L of t equal to 1, 1, 1 plus t times 2, 3, 4. This is a parameterizes the tangent line to path at the point 1, 1, 1. Now, if you plug in time 0, right, what do you get? You get 1, 1, 1. You plug in time 0 to the path, what do you get? Time 0 for the tangent line that I've currently parameterized gives you 1, 1, 1. Time 0 for the path, as it's given, gives you the origin. So at time 0, these two things are at different places. So if you think of the parameter for both curves as both representing physical time, they don't collide. If I want to make the tangent line collide with the path, it's pretty simple enough. I'll make it collide. The formula would be 1, 1, 1 plus, instead of t, replace t with t minus 1. So this is a vector, this is a line with the same direction vector. It's just, we've shifted the parameter so that it matches up. At time 1, now the colliding tangent line, you can easily see that the colliding one is equal to the given one at 1, and they're both at the point 1, 1, 1. I mean, this is kind of an important consideration if you're doing mathematics to describe actual physical situations, right? Like if the parameter of the path actually also has the physical meaning of time, and there's a common time shared by different material objects, it's important that they sync up correctly, right? We always have a freedom to shift the parameter in a given path. Or do weirder things like the example I erased where we had the line which had a variable speed, right? So in any event, so everybody got the attendance? Everybody got to it? Is right? Okay. Just checking. Trying to actually take attendance. So. So I think, guys, if you really look back at how we found tangent lines in Calculus 1 and also Calculus 2 for the parametric curves, this is just the same thing again, right? You find the point, you find the velocity at the point, and you put those two things together to get the tangent line. It's just that. Anybody have any questions about this? The main mistake you guys make is to not pay attention to the fact that we have to evaluate the velocity at the time corresponding to the point of tangency. What I often see, here's the error. Here's a typical mistake that I see people make. Maybe we have r of t is, I don't know, 3t squared cosine t cubed. And here I'll do a two-dimensional one. That's the path. And I say find tangent line at, let's say t equal to the cube root of pi, right? So this, I mixed it up, right? The previous example, I gave you the point of tangency. Now I'm giving you the parameter. So what would the point of tangency be? It would be 3 times pi to the 2/3, whatever that is, and then cosine of pi, right? What's cosine pi? This we should all know without a calculator. Yeah, -1. So there's your point of tangency. And then here's a popular wrong thing people do. They say, the tangent line is parametrized like so. 3 pi to the 2/3. Almost everybody gets this part right. But then they'll tell me something like, and then you do t times 6t, 3t squared, minus 3t squared, sine of t cubed, right? There you go, parameterization of the tangent line. There's just one little problem here, right? That's not a line. I mean, in fact, we'll be able to prove before too long that the curvature of that is not constant. I mean, it's bending and twisting all over the place. This right here, this time varies. This varies. You need this to be a fixed vector of direction if it's a line. The only way this can be a fixed vector of direction is if you plug in the time of tangency. Must plug in time of tangency. And so the time of tangency is I have to set what? T equal to, cube root of pi. So to be correct, I should write L of t, 3 pi to the 2/3 rather, comma minus 1, plus t times 6 times the cube root of pi, minus 3 pi to the 2/3, and, oh, wait a minute, I'm being lazier. That works out to sine of what? And sine of pi is 0, so why am I writing 0? There you go. There is the